Welcome. We are looking at the design of separation systems, and in the previous lecture we got an introduction as what kind of separation processes exist for different kinds of mixtures that emerge from the reactor or from the process. In this lecture we take ahead the theme to see the general guidelines of separation systems design, and this will be followed by certain aspects of distillation column design, which is the most widely used separation process in all types of chemical and process industries. So, here we consider only two types of separation systems, gaseous components and liquid components. We are not considering solid components because separation of solids is relatively easier, and we shall discuss mainly the general structure of the separation system, that is vapor recovery system and liquid separation system. We need to determine the best separation system as a function of the design variables, that is we need to identify the range of variables where we obtain the profitable operation. The first aspect that we need to deal with is the general structure of the separation system. To decide the general structure of the separation system, we need to determine the phase of the reactor effluent stream. The process could be completely vapor phase process, or it could be a gas liquid process or a liquid liquid heterogeneous process. So, depending on the reaction that is occurring, the temperature, pressure, the phase of the reactor effluent is decided. There are different possibilities for vapor liquid processes as below. First is that if the reactor effluent is completely liquid, then only liquid separation systems will be required, such as distillation column, extraction units, azeotropic distillation, etc. However, there will not be any gas absorber, gas absorption unit, etc. For two phase mixture, we can use the reactor as phase splitter, or we can put a flash drum after the reactor where the phase split occurs. The liquid fraction emerging from the flash drum will go to the liquid separation system. If the reactor operates above cooling tower temperature, then we can use the cooling water to cool the reactor vapor stream from up to 30 degrees or 100 degrees Fahrenheit, assuming that the cooling water is available at about 90 or about 90 degrees Fahrenheit, about 20-25 degrees centigrade, and then we have to phase split. If the flash liquid comprises only of the reactants or mostly reactants, but no product component, means our product is mainly in gaseous phase or vapor phase, okay, then that stream can be directly recycled to the reactor. Okay. This is equivalent to a reflux condenser. If the liquid contains mainly products, then we have to send the stream to liquid recovery system. Okay. The low temperature flash vapor is then sent to vapor recovery system, and that vapor mainly contains the unreacted reactant, which are finally recycled to the reactor. If the reactor effluent stream contains only small amount of vapor, then we have to send the reactor effluent directly to the liquid separation system, that is distillation column. Now, distillation column can take various types of feeds, as you have seen in the course of mass transfer, that decides the quality of the feed. If that Q value which is used in distillation, if Q is equal to 1, then the feed is completely saturated liquid or liquid at its bubble point. If Q is less than 1, then it is vapor, and so on and so forth. Okay. If the reactor effluent is all vapor, then we have to cool the stream to room temperature and then try achieving the phase split, or to completely condense the stream. Condensed liquid goes to the liquid recovery system, while the vapor is sent to the vapor recovery system. If the phase split is still not obtained, then we have to pressurize the system so that a phase split is obtained. Okay. Whenever you have the reactor effluent at high pressure and high temperature, first try to reduce the temperature and then reduce the pressure, so that the phase split is easy. Okay. If the phase split is still not obtained, then consider using both high pressure and refrigeration condenser. Okay. If the phase split is not obtained even with refrigeration, then the effluent stream can be directly sent to the vapor recovery system, okay, to take off only the vapor component, that is reactant, and all the gaseous products are then either recycled or they are recycled and purged, so that the inert or whatever are the gaseous components that can be deleterious for the process. It may be like catalyst, poison, etc. Those are the concentration of these components is kept below limit. So, as you see here on the screen, after vapor recovery you can recycle the gas with a purge stream. So, what you see now is a general structure of the separation system. We have a reactor system taking in the feed streams, then the reactor effluent comes out, it is separated. Now, we have shown only the block diagram, we have not shown the details, okay, as what kind of separation system exists, but we can open the second box, this box later on. And then we have product streams, a liquid recycle stream and gas recycle and purge stream. For the liquid streams at the reactor exit, we have a reactor system, then liquid and then liquid separation system. Liquid separation system could be distillation, it could be extraction and so on and so forth. Then if we have a two-phase mixture, vapor liquid mixture at the reactor exit, then we have the reactor system, okay, the liquid goes to the liquid separation system. As far as vapor is concerned, you have to cool to about 30-35 degrees, then you have to phase split. Phase split will generate two streams, liquid stream which is sent to the liquid separation system as shown, and it will generate vapor which is sent to the vapor recovery system. Vapor recovery system will again generate liquid, because you have to recover that vapor, that solute vapor in some solvent, and then the solvent has to be recycled after recovery of solute. That separation or splitting or recovery of solute from solvent is again by distillation. From vapor recovery system, you see a stream that is coming to the liquid separation system. The output of vapor recovery system is non-condensable gas, okay, which is either recycled and also purged, and then liquid separation system will generate again a liquid recycle stream. Okay. So, this is how we can write a general structure of the vapor liquid separation system. You can see also here in the dotted line a stream coming from phase split liquid stream to the reactor. Now, if the liquid contains all unreacted reactants, then there is no reason for separating them, because in one of the previous lectures in the second module of synthesis of flow sheet, we have learnt a heuristic that never separate and mix the two streams. Okay. If the destination of different components is same, those components can be sent in the same stream, and that is exactly what this dotted line is. The reactor exit stream is completely vapor. Then you have a system that is shown on the screen. Okay. Reactor system takes in feed, then the outlet is vapor stream, it is cooled to 35 degrees, then it is sent to phase split. Phase split generates two streams, liquid stream which is sent to liquid separation system, and then the unreacted reactant, the liquid phase is recycled, the products are taken out, and then the vapor stream is sent to the vapor recovery system. Okay. Vapor recovery recovers all the solute vapor, the non-condensable gas is recycled and purged, and again you see a stream coming from vapor recovery system into the liquid separation system for the recovery of solute from the solvent and recycle of solvent to the vapor recovery system. This design of separation systems is based on the heuristic that phase splits are the cheapest method of separation and the assumption that some type of distillation separation is possible. So, all of these systems that we saw are based on these heuristics or thumb rules. Let us see what kind of vapor recovery system we can design and what are the aspects that govern this design. The two decisions that are required for synthesizing the vapor recovery system are: first, the best location of the system, and secondly, the type of vapor recovery system. The location of vapor recovery, we have four choices. The choices are: first, the purge stream, okay, the gas recycle stream, then the flash vapor stream, and somewhere else, none of these. So, these four choices we have for location of the vapor recovery system. Now, depending on the type of process and the type of reactor effluent that we have, the choice will be decided. Now, let us see what governs the choice or the rules for making this decision. If significant amount of valuable material is being lost is in the purge stream, then place the vapor recovery system in the purge stream. Okay. Another reason for this heuristic or thumb rule is that the purge stream has smallest total flow rate. Remember that the vapor recovery system has to recover vapor, the solute vapor from non-condensable gas. But when you are making the design of an absorber, you have to take into account the total gas that is there, which solute plus the carrier gas. So, if the total throughput is high, then the size of the absorber will be high, again more amount of solvent will be required, and then you will have to treat that solvent in distillation column. So, the whole process becomes highly energy intensive. Okay. So, which stream out of emerging out of the flash drum has least flow rate? That is obviously the purge stream, because the stream which emerges out of the flash drum or phase splitter is divided in two parts. One goes to gas recycle, another goes to purge, and purge stream is always smaller. So, when you have place your vapor recovery system in the purge stream, then the size will be smaller, because the purge stream has smallest vapor flow rate. Then secondly, place the vapor recovery system in the gas recycle stream if the material that are deleterious to the reactor operation are present, or recycling some components degrades the product distribution. As I said, the stream which is emerging from the flash drum is split in two parts, purge and recycle. Recycle goes to the reactor. However, the gas recycle stream is usually compressed before recycling to the reactor. So, during that compression some vapor condenses. Now, if that stream contains some deleterious compounds, like as I said earlier, some catalyst poisons or some components which are going to trigger side reactions which will create loss of your valuable reactant. In that case, you to prevent the recycle of these components back to the reactor, you have to place the vapor recovery system in that stream. Now, that stream has the second smallest vapor flow rate. Then thirdly, place the vapor recovery on the flash vapor stream if both 1 and 2 are valid. Okay. The stream that emerges from the flash drum has the highest total flow rate. It contains total non-condensable gas plus total vapor. So, the total flow is highest in that stream. However, if both 1 and 2 apply, if let us say you have to recover valuable material, at the same time you have to prevent the recycling of the deleterious components, then you have to place the gas absorber immediately after the flash drum. Now, in that case gas absorber operation will be expensive, because for the reasons I mentioned earlier. Okay. However, you have no choice, because if you do not remove the components earlier, you are going to suffer greater loss. And then finally, do not use the vapor recovery if neither item 1 and 2 are important. If the vapor recovery system is placed in either recycle or purge stream, then the material balance need to be corrected. Okay, this is because some material that was assumed to be recovered as liquid will be lost in the purge stream, or it might get recycled in the gas stream, which could probably change the compressor size. Okay. So, the material balances need to be corrected whenever we place the vapor recovery system. Here in this diagram, I have shown schematically the logic for choice of placement of vapor recovery system. Okay. We have 3 possible locations after the vapor from the phase split, in the purge stream and in the gas recycle stream. Okay. So, place the vapor recovery system here, I mean in either gas recycle stream or after the flash drum to prevent recycle of certain compounds, and place the vapor recovery system in the purge stream or from the vapor from split to prevent loss of valuable material. After we decide the location of the vapor recovery system, we have to decide at what kind of vapor recovery system we are going to use. The most common choices for vapor recovery system are: first, condensation by compression or cooling or both; then second is absorption, third is adsorption, fourth is membrane separation, and fifth is reactive systems. Now, the basic principles of all of these processes have been covered in the NPTEL course of mass transfer. So, here we shall not go into the basic aspects or basic principles of these processes, but we shall see the practical applicability of these processes under different circumstances. Okay. The choice of vapor recovery system depends on the physical and chemical characteristics of the system in addition to the economic trade-off. As I have mentioned in previous lecture, we are going to have a separate module on economic decision making, and then in that module we shall take the design of gas absorber as the case study. Okay. But here we shall get some basic introduction on this topic. The strategy is that vapor recovery system generates liquid stream that needs to be further purified. Therefore, before designing of the liquid separation system, the vapor recovery system needs to be designed, okay, that will calculate the additional load on liquid separation system in addition to the reactor effluent that is coming out, okay, the products. For gas absorber, where we need to supply solvent to absorber, we introduce a new recycle loop between the separation systems. And finally, we have to estimate the size and cost of each unit to determine the cheapest operation. We have taken in all our previous module or lectures the hydrodealkylation process as the case study, and for hydrodealkylation process, the combined vapor and liquid vapor recovery and liquid separation system is described below. Here the reaction is in vapor phase. I have already told you the temperatures and pressures of the reaction. Toluene reacts with hydrogen to generate benzene and methane. That reactor operates at about 500 psi and about 1200 degrees Fahrenheit or 895 Kelvin temperature. Okay. So, the reactor effluent is a mixture of benzene, that is main product, diphenyl, that is side product, unreacted toluene, hydrogen and methane, and then it is at high pressure, high temperature. First we recover all the heat from that stream, then we reduce the temperature. Thereafter, in the phase split drum or flash drum, we reduce the pressure, okay, to have the split between the gas and liquid phase. Toluene, benzene and diphenyl, they condense, hydrogen and methane, they emerge as the gaseous stream, but they still have vapors of benzene and toluene in it. That is treated, that particular exit stream, gas exit stream is treated in vapor recovery system, and then the benzene and toluene are recovered. You can see here a stream going from vapor recovery system to liquid separation system. This has the solvent plus benzene plus toluene, okay, and then the gas, non-condensable gas that comes out of vapor recovery system is split. You can see here the purge stream containing hydrogen and methane. Now, methane is an inert compound here. So, the concentration of methane has to be kept below a certain limit. So, we use a purge stream, and rest of the stream, this is the gas recycle. The liquid stream generates, the liquid separation system generates streams of benzene and diphenyl which are taken out as product, and then the toluene stream is recycled. So, this is the general separation systems design for the hydrodealkylation process. Now, let us see how we can combine vapor recovery and liquid separation system. If we use partial condenser and flash drum to phase split the reactor effluent, some lightest components will leave with the flash vapor, that is no perfect split in the flash drum, and therefore, will not be recovered in the liquid recovery system. However, if amount of vapor in the stream leaving partial condenser is small, then and if the first split in the liquid separation is distillation, we can eliminate the phase splitter and feeding the reactor effluent stream directly into the distillation column. This is what is possible, because the feed to the distillation column need not be completely liquid. Okay. It may contain some vapor. It might increase the diameter of the distillation column, because the vapor which is coming in the feed also has to be accommodated, but that will take off the phase splitter. Okay. So, you reduce one unit from the process, which will bring down the fixed cost. In this case, the diameter of the column with the 2 phase feed will be higher, as I just showed, to handle the increased vapor load, but at the same time the cost associated with vapor recovery system to remove liquid components from flash vapor will be reduced. Now, there are no heuristics or guidelines available for making such decisions. Okay. So, these decisions vary from case to case, and we need to look at the process carefully before making such decisions. So, this is how you can combine the vapor and liquid separation system. Let us see the design aspects of liquid separation system. What decisions we need to make? I have listed these decisions on the screen. The first decision is that how should the light ends be removed if they contaminate the product. Now, the liquid stream coming in the distillation column will contain some light ends. Means, for example, if you consider a petroleum refinery, then these light ends are usually C1 to C4 components. Okay. Usually methane, ethane, ethylene, propane, propylene, butane, butene, butadienes. Okay. These are the light components. Okay. Now, these have to be removed before you start your main distillation operation. Okay. Then, so the first question is how should the light ends be removed? Secondly, what should be the destination of the light ends? What should we do with these light ends? Then thirdly, what about the azeotropes? Because it is very likely that there will be either binary or ternary or even quaternary azeotropes. Okay. So, to separate the azeotropic components, we need to have another supplementary separation system to distillation. Okay. Then, how do we recycle components forming azeotrope, or should we split them? Now, in some cases, if both azeotrope, like if the complete azeotrope is going back to the reactor, then there is no need to split it. Okay. However, in some cases, for example, like ethanol water system, to obtain 99.99% ethanol, pure ethanol, so as to blend it with petroleum, you have to separate water using pervaporation, which is a process supplement to distillation. Ethanol and water form azeotropic mixture at about 82% of ethanol. So, distillation purification of ethanol beyond that percentage is not possible. So, you have to go for alternate removal of water, remaining water. So, the splitting of the azeotrope is a major decision and it is highly cost intensive. Okay. Which separation fourth decision, which separations can be made by distillation? You would like to have as many separations by distillation as possible for two reasons, although distillation is energy intensive process. Firstly, the distillation columns can be integrated with the process, and secondly, they are easy to design and operate. Okay. Even if they are energy intensive, you can combine the reboiler with some other process stream which has higher heat content or surplus heat and drive that reboiler. So, that way the distillation columns are easy to heat integrate with the process, that is one thing. And secondly, the design is easier, because once you have, it is a operation which has more than 100 years of history. So, it will be very easy to design and operate and optimize the distillation column as per your requirement. Okay. Then, what should be the sequence of separation of components by distillation? Okay. If you have a multi-component mixture, then how should you separate them? And then what is the alternative separation to distillation if distillation is not feasible? So, these are some of the important questions that you will face while designing the liquid separation system, and you have to make decisions on it. We need to make these decisions as a function of the design variables over the range of potentially profitable operation. Now, let us see the first thing, light ends. Light ends will be dissolved in the liquid, leaving the phase splitter, as well as the liquid streams leaving the vapor recovery system. If these contaminate the product, then they should be removed. Now, what are the alternatives to distillation for removal of light ends? First option is obvious: drop the pressure in the flash drum itself or increase the stream temperature and remove the light ends in the phase splitter. The solubility of these light ends are essentially the gases, as I told you. Their solubility decreases with temperature. So, if you increase the temperature or if you reduce the pressure, then also this desorption occurs, okay, and then you can remove the light ends. or you can use a partial condenser in the product column of the distillation column, so that only the heavier components like C5, C6 onwards they condense, but not these light ends. Then use a pasteurization section on the product column with a side stream, or use a stabilizer column before the product column. Stabilizer column means simply boiling of the reactor, the mixture, liquid mixture, so as to desorb all the gases. So, what I have shown here are the schematics of these three types of removal of light ends: a partial condenser, then a stabilizer column, and a pasteurization column with a side stream. Okay. The options for removal of light ends are listed in order of increasing cost. So, partial condenser is the cheapest, then comes the stabilizer column, then comes the pasteurization column. To make a decision on the light ends removal, it is necessary to know the flow rates of the light ends and to make the shortcut calculations. The vapor stream is recycled to the vapor recovery system. Okay. So, that is what it is. So, in order to have a decision on the removal of these light ends, you have to make certain calculations. Okay. First of all, you have to know what is the flow rate of the light ends, and then you have to do some shortcut calculations. Once we decide that, then the next question that we face is the destination of light ends. A possible destination of light ends is just a flare system. You burn them before emitting, like convert them to carbon dioxide and water, and then this is the gas is flared. But because of this greenhouse gas emissions, the flare systems are now being questioned. Like in many countries, especially in the Gulf countries, the flare of these gases is taxed because it is adding CO2 or greenhouse gas to the atmosphere. The alternate use is that use them as fuel in the process, send the light ends to fuel or recycle light ends to vapor recovery system or to the flash drum. Okay. So, these are some of the options. Like for example, methane, if the light ends are saturated molecules like methane, ethane, propane, like propane and mixture of propane and butane is used as a LPG. Okay. So, that is one of the use of these light ends. Now, if as the unsaturation of the molecule increases, the reactivity increases. So, molecules like ethylene, propylene are increasingly being used as the major feedstock for petrochemicals. So, these are recovered and these fetch good market prices. Butene is also used as a reactant, and butadiene is a monomer for butadiene rubber, styrene butadiene rubber. Okay. So, these are some of the possible destinations or uses of the light ends. Okay. For very little value of light ends, remove them from the process through a vent and then use them basically as the fuel in the process. If venting causes pollution problem, then try venting the light ends through a flare system so as to burn the offending components. If the light ends are flammable, then try to recover the fuel value by using them as a fuel in your furnace or other heaters. And lastly, if the light ends are valuable, then retain them in the process, like some of the valuable light ends I just mentioned, the unsaturated molecules. Okay. If these are recycled to the vapor recovery system, we introduce another recycle stream in the process. But remember that this recovery of the valuable light ends come at a cost. Okay. Okay. So, summarizing, no contamination of product by light ends, merely recycle them to the reactor with a reactant recycle stream, or remove them from the process with the byproduct stream and send to fuel supply. Method of removal and destination of light ends depends on the amount of light ends that I already mentioned. So, the determination of amount of light ends as a function of design variables is must before making a final decision. Okay. This point we note. Azeotropes with reactants. If a component forms azeotrope, we have choice of either recycling it or splitting it. If the component forms azeotrope with reactant, then we have trouble, because if we have to recycle the unreacted reactant to the reactor, the azeotrope component also gets recycled. Okay. Then we have to split the azeotrope. If the azeotrope forming component is deleterious, okay, is going to trigger side reactions or is going to have some adverse impact on the process, we have to split the azeotrope to recycle just the reactant. Azeotropic distillation, as I already mentioned, is an expensive operation, because to break the azeotrope you have to, many times you have to use a third component called as entrainer, and then you require two columns. Okay, first column to make the azeotropic distillation, and second component is to recover that entrainer and recycle. For recycling the azeotrope, all equipment in the recycle loop must be oversized to handle the incremental flow of extra component. That cost you are going to incur if you want to decide you want to recycle the azeotrope. The general guidelines and heuristics are not available for making this decision, and the final decision over this depends on the exact process and varies from case to case. Okay. The next question is that how long distillation will be applicable? Like as I said, distillation would be the most preferred method of separation of liquid, but will distillation be possible each and every time? In general, distillation is an energy intensive, but if you heat integrate the process, then the cost goes. So, it is less expensive means of liquid mixture separation compared to other processes. For example, in liquid extraction, okay, you need to recover the solvent. So, you need a distillation column there. If you want to go for a membrane process, then membrane itself is a highly expensive component. So, if you compare, although distillation is energy intensive because you have to use reboiler and condenser, if you compare distillation with these other things, distillation still stands a good chance. Okay. So, that is what distillation is a comparatively least expensive means of liquid mixture separation. For close relative volatilities, neighboring boiling point or alpha equal to 1.1, distillation can become expensive because of the large number of plates that are required, or you have to use high reflux ratio, large vapor rates, large column diameter, and which comes as a consequence large condenser and reboiler with high heat duties, and basically heat duties means large steam and cooling water cost. So, that is what means distillation has that limitation. If as the alpha becomes closer to 1, like 1.1, 1.2, then you have this problem that very large number of plates would be required for separation of the mixtures. A typical rule here is that for neighboring components having relative volatility less than 1.1 in the mixture, group the components and treat the group as a single component. Okay. So, this is a sort of a rule, or you can say heuristic. It may not be applicable every time, but this is what usually the designers or engineers do. Okay. If the relative volatility is less than 1.1, then you treat that mixture of components as a single entity, try to remove all other things, and once everything is removed, then you try to split that mixture. We have to develop the best distillation sequence for the group and other components, followed by separation of the lumped components using other procedures. So, what I have shown here is an example distillation separation. We consider 5 component mixture, okay, A, B, C, D, E, and alpha is given with respect to D. Now, D is a heavy key element, okay, which is an important element among all the heavy components. So, alpha value is taken 1 with respect to D. So, E being a heavier component, more boiling point, it has a alpha lesser than 1. Okay. Now, with respect to D, C has alpha of 1.6, B has alpha of 1.7, A has alpha of 3.2. Now, if you calculate the intermediate volatilities, okay, you can see that you have a very low volatility, relative volatility between B and C, okay, because alpha BC is essentially alpha BD divided by alpha CD, and then 1.7 divided by 1.6 is very close to 1.1. Okay. So, here you have the problem. Now, what I have shown as side is the best sequence for the separation of such kind of mixture. In the first column, all the 5 components go in A, B, C, D, E, A is taken off, and then B, C, D, E flow to the next column, in this column, the top product is a mixture of B and C. Okay. As I said that when components have very close boiling points or very alpha very close to 1, treat those 2 components or 3 components whatever as a single entity. So, we take off BC together at the top of column 2, okay, and then the remaining 2 components D and D flow to the third column, and then they are split as individual components D and D. Now, as far as this BC mixture is concerned, okay, it is taken off as the top product of the second column, and then it is sent to a separate process, which could be liquid extraction, which could be let us say membrane separation, etc., and then the 2 components B and C are separated, or here there could be another azeotropic distillation using an entrainer. Okay. So, this is how you would like to treat the azeotropic mixture. So, if at all you have to split the azeotrope, if splitting of azeotrope is at most necessary, then you do it in absence of all other components. So, that you are handling the least total load, liquid load, and there is no other component which can complicate your process. Let us see the sequencing of distillation column, because this is another major question that you are going to face while designing the separation system. We first consider the design of distillation systems comprising of simple columns. These simple columns are associated with one feed split into 2 products, then key components adjacent in volatility, and a reboiler and a condenser, which is given independent utilities, means there is no heat integration as such. Now, if there is a 3 component mixture and simple columns are employed, then we have 2 possible sequences for separation. Okay. The first sequence is shown here. The mixture of A, B, C components flows to the first column. A is taken off as a distillate and B and C go to the next column, and then they are split into individual mixtures B and C. Okay. This is known as a direct sequence, and the characteristic of direct sequence is that the lightest component is taken off overhead in each column. So, the mixture is separated sequence of higher volatility. Okay. That is how, like A then B, like that. Another option is that in the first column the mixture ABC will flow, but C will be taken off as a bottom product. Okay. And then A, B together are taken off as the top product, which move to the second column, and then they are split individually. Okay. So, this is not in the direct sequence, direct like proportion of the relative volatility. A and B are taken off together. Okay. So, heaviest component is taken off or removed in the first place. So, this sequence is known as the indirect sequence, where the heaviest component is taken off as the bottom product in each column. This is another option that we have. Although these sequences look similar, they are not same, but they are similar, there will be a significant difference in the capital and operating cost of these 2 sequences. As the number of components in the mixture rise, then the complexity of separation increases. So, for a ternary mixture, we had 2 possible sequences. As the number of components increase, then we have more and more possible sequences. Now, what I have given here is example for a 5 component mixture, like instead of ABC, let us say we have 5 component mixture A, B, C, D, E, then there are 14 possible sequences, and these 14 sequences are now on the screen. First, ABCD mixture, the direct sequence, where the components are removed in the order of the volatility. Okay. Like the first sequence, A is taken off first, B is taken off second, C is taken off third, and then D, E is split. After removal of B from ABCD, after removal of A and B from the ABCD mixture, we are left with a ternary system CDE, and now CDE can be split in direct and indirect sequence. So, the first one that we just saw was a direct sequence. There could be an indirect sequence also, like C and D taken off as the top product and E taken off as a bottom product in the third column, and then mixture CD is split individually. Okay. Now, another sequence is that after removal of A, you are left with a quaternary mixture B, C, D, E, then you split as mixture of two components like BC and DE, and then you are left with two binary mixtures BC and DE, and then these are split individually into components and two columns BC and DE. Then after removal of A, you have another choice of splitting the quaternary mixture in indirect sequence like BCD together taken off as the top product, E taken off, the heaviest component taken off as the bottom product, and then the mixture BCD is split again in direct and indirect sequence. So, in this way you can write 14 different sequences, okay, which are shown. You can yourself try to write these sequences, you can take this as an exercise and the answer is already with you, and then you try to make your own sequences and compare with the answer which is there on the screen now. Okay. Now, as the number of components further increase, the complexity even increases. For example, if you have 6 component mixture, then you have as many as 42 different sequences, and choosing between the sequence is now a major decision. When as the number of alternatives increase, the difficulty in making decision also increases, because you have to evaluate the cost associated with each of the sequence, and there are two costs. First is the fixed cost and second is the operating cost. Okay. Now, heat integration may also affect the operating cost significantly. Heat integration can be achieved within a separation sequence as well. So, everywhere you are going to require 4 columns. So, is it possible to couple these columns? For example, is it possible that you increase the operating pressure of one column so that the condensing temperature of the vapor increases, and then you try to condense these vapors in the reboiler of the second column, okay, by reducing the pressure there, so that you create sufficient temperature difference in the reboiler. Suppose it is a kettle type of reboiler, then you have to have always nucleate boiling, you have to avoid film boiling. To have nuclear boiling, you have to have delta T at least 40-50 degrees centigrade. So, that temperature difference, all these things you have seen in the course of heat transfer in NPTEL. Okay, so, these are, as I said, we are not here to learn principles, but only application. So, in one column you increase pressure so that the condensing temperature of the vapor increases. In the second column you reduce pressure so that the boiling point of the liquid decreases, and try to achieve the desired delta T to have the heat integration. In addition to this, there could be heat integration from other parts of the process. As I said, like for example, take the HDA process. The stream which emerges from the reactor is at very high temperature and pressure. So, it has sufficient heat in it to drive the reboilers of all the columns. Okay. So, that heat integration is also possible. Okay. You try to condense, you try to couple this the streams with surplus heat with the reboilers, or let us say if you have cold streams, then those can run your condensers and try to achieve heat integration, so that the operating cost goes down. Okay. The simultaneous optimization of sequence together with heat integration is required. So, while choosing the sequence, this is another factor that will come into picture. There are some practical constraints. Although one sequence may look significantly better over other, okay, there could be practical constraints. Now, what are these constraints? Okay. First is the safety consideration. Hazardous components to be removed from the process as early as possible to minimize the inventory of that material. Okay. So, even if one particular sequence has higher energy integration possibility or least cost, if it if it has a hazardous component which stays in the process for longer time, then you have the problem. So, you may have to go for another sequence which removes this component early. Okay. Then, if any component is highly reactive or heat sensitive or likely to be degraded fast with heat, then it should be removed as soon as possible. So, try to get that sequence which takes off that particular material in the first or second column itself. Then, third is corrosive material. These need to be removed early, because like when we talked of sequence, we never talked of the material of construction or like other details. Okay. Now, A, B, C, D, E all together may not be may not have same properties. Like for example, is component E is highly corrosive. Okay. Then for the distillation column treating A, B, C, D, E mixture, you may require plates and shell made up of stainless steel, this SS302, 304, okay, which is an expensive material. So, and as long as E remains in that flow stream, everywhere you will have to have that material. So, although the sequence which is a direct sequence, which removes E in the very last column, may look attractive from energy integration point of view, from the mechanical design of the columns is concerned, you have to go for sequence which removes E as soon as possible, because you have to, if you keep E in the process for long time, you have to design all columns made up of expensive material, that increases the fixed cost. So, somewhere trade off is important, okay, you try to achieve trade off between fixed cost and operating cost. So, that is it. Then if the decomposition of certain components in the reboiler is likely to happen, or it is likely to contaminate the process, then no finished product can be taken off from the column bottom. So, you have to remove these components as soon as possible. For compounds that are likely to undergo polymerization during distillation, you have to take special care. In this case, certain chemicals are added, like hydroquinone is one of the chemicals which are inhibitors, okay, which inhibit the polymerization. However, these chemicals are usually high boiling components, okay, and these inhibitors end up in the bottom of the column and they contaminate the product there. Okay. So, in this case, the finished product cannot be taken off from the column bottom. Okay. Then, in the column to us, in the feed to a separation sequence, some components which are difficult to condense require low temperature or refrigeration or high pressure for total condensation. In such situation, try to remove them as soon as possible. Okay. Try to remove them from the top of the first column itself, so as to minimize the cost of utilities, okay, because the longer that you keep them in the process, in every column you may require refrigeration or high pressure, which are expensive utilities. So, in order to limit the operating cost, you have to remove them as soon as possible. Okay. There are some basic heuristics that I will mention here. Okay. We shall see these things in greater detail in the next lecture, okay. But I am just mentioning these heuristics for selection of column sequence for non-integrated columns, which means we are not considering the heat integration at this moment. Okay. So, there are 4 common heuristics. First, separation in which the relative volatility of key components is close to 1, or the mixture which exhibit azeotropic behavior should be performed in the absence of non-key components, which I just mentioned, that whenever you are splitting this close boiling mixture, try to have as little contamination from other things as possible. That means, you keep them and as a last separation, okay, or do the most difficult separation last. This is first heuristic. The second heuristic is that sequences removing the lightest component alone, one by one in a column, overhead should be favored, or the direct sequence should be favored. The components removed in the order of their relative volatility, highest relative volatility first, followed and decreasing relative volatility. Then thirdly, a component comprising of large fraction of the feed should be removed first. This is to limit the total volume that you are handling at any time, okay, that because every time you have to pump this much of liquid, that increases the pumping cost, that you have to boil that liquid, that increases the energy cost. Okay. So, in other words, separation with the highest percentage recovery should be done last. And then fourthly, you have to favor near equimolar splits between top and bottom product in individual columns. This helps in energy integration, to have nearly equimolar split between top and bottom product in individual columns. But remember that these are only heuristics, these are not laws or rules. These are only heuristics, these are thumb rules which have been devised on the basis of observations made in many practical applications. So, these have come out of experience. Case to case basis, these may vary, okay, like all of these heuristics may not be applicable in each case. So, depending on the process that we have, okay, depending on the flow rates and selectivity, many factors, you have to decide the column sequence. So, in the next lecture, we shall see an example of deciding the column sequence. Another thing that you will see is that all these heuristics are qualitative, okay, they do not give any quantitative answer. So, we shall see as how these heuristics could be applied in the best possible way for separation of any mixture, and if these heuristics are not applicable, then what other guidelines could be used for deciding the column sequence.